Hello, everybody, and very welcome to this webcast on modeling and analysis of non-conforming joints in the AnyBody modeling system. My name is John Rasmussen, and I am the presenter of this webcast, and I'm the guy standing there on the left-hand side. Michael Damsgaard is the host of the event, and he is trying to make sure that the technology is working, and he is the well-dressed guy there on the right-hand side. Now, one of the advantages of webcasts is that you have the opportunity to ask questions as we go along. So if there's anything that I say which you think is mysterious or anything that you would like to have clarified further, then you can just go ahead and ask the question. You don't have to wait until I stop talking. The way that you can do this is if you look at the lower right-hand side of your screen, you should see a little WebEx panel. And there is a button with a question mark. If you click the question mark on that panel, you will get a question and answers panel popping up. And into that panel, you can type your question. When you finish typing your question, please send the question to host, presenter, and panelists. And then we will try to answer it as well as we can. Now, if the question is a simple one, then we are going to try to answer it right away. And the answer will pop up in your question and answers panel. If we think that the question is so good that it has a general interest for the rest of the audience, then we're going to postpone it until the end of the session, and then I will try to answer it orally here. So please don't hold back. Please don't hesitate to ask questions whenever you want to. Now, I would like to begin this with the laws of Newton. We have implemented some new technology into the AnyBody modeling system, and we are pretty excited about this technology, actually. And to explain to you what it is, I think the best way is to start with the laws of Newton. Now, the laws of Newton in their simplest form are the ones that you see here in front of you. Newton's second law, force equals mass times acceleration, is valid for a particle. Obviously, for a musculoskeletal system like the ones that we analyze in AnyBody, it's quite a bit more complicated than that, and the equations look slightly different, but they're basically the same. Force equals mass times acceleration. Now, this means that if we know the acceleration, meaning that if we know the movement, then we can find the force. And below, on the other version of Newton's second equation down here, you can see that if we happen to know the forces in the system, then we can find out what the acceleration is. But the point here is that either we have to know the motion, and then we can find the forces, or we have to know the forces, and then we can find the motion. If we know the motion and want to find the forces, then we're basically doing inverse dynamics. And this is what AnyBody is normally doing. And the big advantage of that is that it makes it easy to find out what the muscle forces are. The other option is you can do forward dynamics. Now, forward dynamics has the advantage that you can handle some complex phenomena, namely examples or cases where you don't know exactly what the movement is. But the disadvantage is you have to know what the forces are. And if you don't know what the muscle forces are, then you have to get into very complicated calculations and very time-consuming calculations to figure that out. Now, this turns out to be sort of a catch-22 problem, and I'm going to try to explain why. And so just to recapitulate, forward dynamics can handle contact and other complicated phenomena that are influencing the kinematics, but motion forces are difficult to deal with. And inverse dynamics, which is what AnyBody normally does, it handles motion forces really well if the movements are known. But we have a problem with non-conforming joints because in non-conforming joints, we typically have small motions that we don't know in advance and which depend on the muscle forces. So we can't determine those motions before we know the muscle forces, and we can't determine the muscle forces before we know the motions. So that is basically the problem that we're trying to address here. Now, non-conforming joints in the body are in many different places. I have listed 3 examples here. The most well-known probably is the knee, and we'll get into much more detail with the knee in just a few moments. Another example is prosthetic shoulders, which are often very loose and in which you have typically a superior migration of the humeral part of the prosthesis when the arm is elevated. And another example is the temporomandibular joint, so that's the joint between the mandible and the skull. And this is also a quite loose joint that allows you to move your mandible in many different directions when you're chewing. Another example is the joints in the spine. So these are, as you know, the spinal vertebrae are connected by elastic discs. And because these discs are elastic, it means that the deformations in the discs depend on the forces that we apply to them, and the muscle forces in the spine are a very important contributor there. So again, we have the case that we don't really know what the motion is before we know what the muscle forces are. So this is what we're going to address, and the reason why we're having this webcast is actually that we have come up with a solution, and we think a very elegant solution that allows us to simulate in vivo muscle forces as well as handle micromotions in joints that we don't know in advance. So this means we can now handle non-conforming joints. Now, let's take a look at the knee as an example. Now, why is the knee a non-conforming joint? Well, first of all, you can see that the joint surfaces are incongruent. So you have one joint surface is this one that I'm trying to highlight here, and this is the surface of one of the tibial condyles, and you can see that this is a curved surface that has a variable radius of curvature. And the other surfaces down here, this is the tibial surface, and this is much more flat, and therefore you have a non-conforming joint because it actually allows the femoral condyle to slide back and forth to some extent on the tibial plateau. And this means that the movement of the tibia with respect to the femur will depend on the applied forces. This is very well documented in the literature with sophisticated examples and sophisticated experiments, and we can be quite sure that this is the way the knee actually works. So what is it actually that stabilizes a non-conforming joint? Well, you see in the case of the knee, even though the knee is non-conforming, there is still some stabilizing factors, because otherwise the lower leg would fall off the thigh, and that doesn't happen. So there must be some stabilizing elements in the knee that actually keep it together. And of course, those stabilizing elements can be the forces between the bones. This is what in classical biomechanics is often called bone-on-bone contact forces, and that is one of the things that are keeping the knee stable. Even though the surfaces are not congruent, you can see that we can get reaction forces that point in different directions, like I have indicated here. The other stabilizing factor is the meniscus. So the meniscus is also kind of embracing the femoral condyle and providing some additional stability. The meniscus is made of a soft material. It's basically made of sort of cartilage, and so it's a relatively soft material, so it's compliant, and it means that it is able to deform with the forces that is applied to it. The final thing that stabilizes the knee is obviously the ligaments, the cruciate ligaments and the two collateral ligaments in the knee, and those are also elastic elements. They're made of relatively soft material. So again, the forces that are applied to the knee will cause deformations of these materials, and that will cause micro deformations in the knee. And so the question is, what are these deformations, and how do they depend on the muscle forces, and can we somehow handle the fact that the muscle forces are influencing what these deformations are? Can we somehow handle that together with the necessity to compute the muscle forces, so as we balance a given external force? The answer is, of course, yes, because otherwise we wouldn't be having this webcast. And I'm going to explain to you how that happens. In addition to handling these elastic elements, we also need a way to handle the contact problems that happen in non-conforming joints. And what you see here is a simple version of what we might perceive as a total knee replacement implant. And you can see up here we have the femoral part up here, and then we have the tibial part down here. And we have made them semi-transparent, these two, so that you can see inside that we have a distribution of contact forces in here. And what this actually is, it is a kind of a contact element which will determine based on the displacements of the different parts. It will determine the forces that are acting between them. Now, these two surfaces can have any shape that we like. They are just triangulated surfaces, and they can comprise as many triangles as you want. In fact, if you look at the little arrows in here, you can see that there are many of these arrows, and there's one arrow basically in each corner point of the triangulated mesh that will make up the contacting surfaces. So we're also going to look into how we do this a little later in the presentation. So we're going to do two demos. So basically the presentation today will mostly be comprised of demos. And the first demo we do is rather detailed, and that's the one that we are going to spend the most time on, because that's going to show you how in 3 simple steps we convert a simple model that does not use force-dependent kinematics, how we convert that into a force-dependent kinematics model that will determine the micromotions in the knee. So this we're going to do in detail, and we're going to go into how the model is defined in AnyBody. And then we're going to do a quick one afterwards in the interest of time, where we are showing how we can add the 2 surfaces that I showed you on the previous slide, representing bony surfaces or prosthetic surfaces. Both of these examples I'm going to show you here are going to be relatively simple. And they're not going to be really anatomically realistic. However, we have a new webcast scheduled on September 29th. And in that webcast, we are going to skip the methods because we are going to cover them in this webcast. And then in return, instead of going into the methods, then on September 29th, we will look into anatomically realistic models of these non-conforming joints that we are developing at the moment. So please stay tuned for the webcast on September 29th. Now, the example that we're going to do here, in the interest of time and because we need to be able to analyze it in real time as you're looking here in the webcast, has to be a rather simple one. So it is actually the example of a new tutorial that we're going to release with version 5.1 that's going to be available in a few days. And it has a very simplified version of the knee. But the simplified version of the knee has some characteristics in common with the real knee. So we are going to define, as you can see here I'm just going to try to make a better pointer here. As you can see over here, you can see that the tibial plateau is just a flat plateau, and the femoral condyle is just a circular sphere over which we also have the quadriceps muscle wrapping. So this is a model that only has one muscle. It doesn't really matter. We could have as many muscles as we wanted to, but we just defined this one muscle to make it a really quick and simple model. And then there's a contact condition between this femoral condyle, this circular femoral condyle, and the flat tibial plateau. And this contact condition is such that it is elastic. And there's one elasticity represented by this spring that I'm pointing to here, which is normal to the tibial plateau or perpendicular to the tibial plateau. And then there's another one represented by this one, which is the elasticity in the direction parallel to the tibial plateau. Obviously, these have different elasticities. This one is probably more rigid than the one in the shear direction. The one in the perpendicular direction is actually representing the elasticity of the cartilage between the femur and the tibia, and the one in the tangential direction is representing the stiffness of the meniscus and the cruciate ligaments. So that's the way we can think of this. Now let's go on and try to define this model. So I'm going to close down the presentation right now. I'm just going to discard my annotations and close down the presentation like this. And then I'm going to go and open up the AnyBody modeling system. And I'm going to load a model which is just a standard AnyBody model, the way that we would normally have done it this is the model that I have loaded, and I'm just going to run it. It runs very quickly. So we select the inverse dynamics and we run it, and you can see that this model has a knee in the middle, and it has a tibial part and a femoral part up here, and then it has one muscle which is making those two parts move with respect to each other. The blue guy here in the middle is the femoral condyle. However, this model that we see here is not one that uses force-dependent kinematics. So we're going to go through 3 simple steps now that will convert this into a force-dependent kinematics model. I'm first going to switch this off so that the femoral condyle is no longer visible, but we know it is there, and because it allows us to look inside the knee. Then I'm going to go over here to my model, and I'm going to perform 3 steps that will make this a force-dependent kinematics model. The first thing I'm going to do is I'm going to go down into the study section of the model, and I'm going to specify that I want to use force-dependent kinematics analysis. So if I go to model and study here, I can go into the inverse dynamics here, and I can find a property here which is called force-dependent kinematics on-off. I'm just going to insert that and erase the parts in front here that we don't need. And then I'm going to write equal to, and then I'm going to set it on. So now the force-dependent kinematics is switched on. If I load the model again, and I run the model again, then you won't actually see any difference from what we had before. Because I have switched on the force-dependent kinematics, but I've not done anything to the joint. I've not added any elasticity in the joint yet. So those are the 2 last steps that I have to do. I'm going to go up into the joint, and here you see we have the knee joint. Right here is the definition of the knee joint. So what this says is this is a revolute joint, and it is a revolute joint that connects the shank knee center node with the thigh knee center node. And this is all fine, but we're going to try to change that joint so that we can get a force-dependent kinematics solution in the problem. First thing we're going to do is we're going to open up the joint. I can go over here in my model, close the study part again, and open up the model part. And then I go down and find my knee joint. And I'm going to look into some properties in the knee joint. What I'm going to be interested in is the constraints part, because that is the part of the joint that actually determines how the joint is kept together. So we're going to modify 2 things inside the constraints folder here. So I'll open up the folder. And since I know I'm going to change that, I can write here constraints equal to, and then a couple of braces that mean that anything I do now inside these braces will modify the constraints in the joint. The first thing I'm going to do is I'm going to look at the C type here. And I can just insert that object name. And I don't need anything but C type because I already said that we're in constraints. And if I double click it over here, we can see what the value is currently. And you can see the value is currently this. It is a revolute joint, and therefore it has 5 components to it, and they're all hard. And hard means that it's a hard constraint, so we don't really accept any sort of violation of this constraint in the model. However, when we do force-dependent kinematics, we have some elasticity in the joint, so we have to allow for violation of the joint constraints. And therefore, the 2 first of these we're going to redefine from being hard to be force-dependent. Force-dependent, like this. So this means now that the local X direction and the local Y direction in the joint are now force-dependent constraints. Remember to add a semicolon at the end of that. The other thing that I have to modify in the joint is that I have to go into the reactions. And if we look at the reaction types, I can insert that as well. So I have reaction.type, and if I double click that, we can see what they are at the moment. So you can see that reactions in the joint are now switched on. Now the meaning of this is that in a hard constrained joint, we want the joint to provide the necessary reaction forces to keep the joint exactly at the place where it's supposed to be. That is the nature of a hard joint. And to do that, we are defining reaction forces inside the joint. I'm going to take a copy of this, and then I will insert it over here. And then for the 2 degrees of freedom that we have now defined as force dependent, I'm going to switch those reactions off. This means that now there is no longer any reaction inside the joint that makes sure that the joint constraints in these 2 directions are actually maintained. And this is the elastic forces in the joint. So instead of those reaction forces, I'm now going to do as the 3rd step of converting this model into a force-dependent kinematics model, I'm going to define an elastic force that is acting inside the joint and which is a function of the displacement in the joint. So this is the nature of an elastic force. It's going to be proportional to the displacement in the joint. That is the simplest type that I can make this linear elastic model. I could also make any sort of nonlinear elastic model, but I'm just going to do a linear one now. So what I will do is I will go over to my classes section and open up the class list, and then I'm going to find an object called an AnyForce, and I'm going to insert that in here. And an AnyForce is an object that can work on any kinematic measure, and a kinematic measure is basically anything we can measure, any distance or any other thing we can measure in an AnyBody model. So we're going to call this knee elastic source, and I have to specify which kinematic measure this is going to work on. And I very conveniently have a measure inside the joint that I can use. This is the measure that measures the constraint violations inside the joint. So I can go back to my model, and I can find my knee joint, and inside the knee joint I can find a linear measure. This is the one I have here. So I can find right here my linear measure. I give it some name, some local name, and I say this is just going to be pointing at the linear measure inside my knee joint. So now I have a measure which I will allow, which measures the displacements inside the knee joint, and those displacements I'm going to penalize with some elastic forces. And this is what I do here. So the force vector I'm going to define has to be a 3-dimensional vector, because the linear measure I have here is also a 3-dimensional vector. It measures in the x and the y and the z direction. So I'm going to write here minus 1,000 times limb dot position. This is the position of the limb joint, and then the first component, this is the displacement in the local x direction. This is the one which is parallel to the tibial plateau. And I'm going to write minus 5,000 times limb dot position 1. And this is the second direction inside the joint, and this is the direction which is perpendicular to the tibial plateau. And then finally, in the z direction, I'm going to write 0, because we didn't actually turn the z direction into a force-dependent kinematics direction, so there's no reason to add any force there. Now notice that I have used 1,000 here as my spring constant, and I have used 5,000 over here. This is because I'm expecting that the joint is going to be more rigid perpendicularly to the tibial plateau than it is in parallel with the tibial plateau. So in this case, I have presumed that it's going to be 5 times more rigid perpendicularly to the tibial plateau. The constants that I have used here are probably quite small. Now, 1,000 means in this model, because it is using SI units, that if the displacement is 1 meter in the joint, then I will get a reactive force of 1,000 Newton. Obviously, 1 meter would rip any knee apart, and so if we thought of this as an elastic force, the elastic force would be much larger than that. I actually have no idea what the real values here are, but we could figure that out by means of cadaveric models or by means of finite element models of these, and then we could simply insert the correct values. We could also actually insert nonlinear functions here. It wouldn't matter. The whole analysis is not linear. It is completely nonlinear. So we could insert any kind of nonlinear function that we wanted here. But anyway, these small values mean that we're going to get some nice big displacements that we can look at, and that makes it a little funnier to look at the analysis in just a second. Let's try to load this and see whether I did everything right. So I click the load button again, and as you can see, it has loaded successfully down here, and it took just a brief moment to do so because it's a very simple model. Then I can go over here to the inverse dynamics. I can start running that. And now this has been converted into a force-dependent kinematics. I'm just going to switch this one off, this condyle off, because that will allow us to see what actually happens inside the knee. I think I'm just going to run the initial conditions first. See, now the whole thing fell into place. And then you can look at it exactly from the side. And you can see this sphere right here is the two nodes of the tibia in the knee and the femur in the knee respectively, and the revolute joint we have is trying to keep those on top of each other. But of course the reactions in the low direction and right direction have now been switched off, so they're actually going to have some displacements. And so pay attention to this sphere here, which is going to turn into two spheres as soon as we start the analysis because of the elastic deformation in the knee. So we start the analysis here, and you can see that first the muscle force is not very large, and we do not get very big displacements in the knee. The two spheres are pretty much on top of each other. But now we're beginning to get a little more force, and you can see that now one sphere is starting to deviate from the other one. And this is, of course, because the loading in this model is only gravity. So initially there wasn't really any loading on the tibia. But now, as the tibia is being extended, the gravity is acting on the tibia, and there is more for our muscle to do. The muscle will be pulling more on the tibia, and because of the elasticity in the joints, you can see that there is now a difference between the locations of the two surfaces. So if we look closer here, you can see that now this sphere here is deviating from the other sphere, and this is the elastic displacement we have in the knee. You can also see that most of the displacement is actually kind of parallel to the tibia. There is not much displacement in the tangential direction or in the shear direction parallel to the tibial plateau. And the reason for that, of course, is that most of the force that is generated here is generated by the quadriceps muscle. And you can see the quadriceps muscle is pulling almost parallel to the line of the tibia. And this is probably quite important also in real knees. If it didn't do that, we would probably always suffer ACL injuries much more often than we do. So now the knee is getting extended, and we just have about 10 time steps to go, and then we're going to look at the results. Obviously, the quadriceps muscle has to pull harder and harder, and so we get more and more displacement here. Okay, so now it's done, and we can inspect the results that we have obtained. So we go to our chart window here, and we can go into the model, and we can take a look at the knee elastic force, and we can take a look at the linear measure inside the knee elastic force. So this is the one that is actually measuring the displacement inside the joint. And the red graph here is in the X direction, so that is in the direction which is in parallel with the tibial plateau. You see there's very little displacement here. And the green one is perpendicular to the tibial plateau. Now, of course, now we can start playing around with the model. And we can start seeing what happens if we change different parameters in the model. So, for instance, what would happen if I change the insertion point of the quadriceps muscle so that it doesn't insert here on the frontal aspect of the tibia, but rather inserts in the middle of the tibia? This would mean that the muscle would pull more forward, and probably that would create more shear force. Let's see whether that is actually the case. So I go back to the model, and I find the definition of the tibia, which should be up here. And there's the thigh, and here's the shank. And I go to the shank here, you can see the quadriceps insertion node. And here's the first coordinate. This is the displacement in the frontal direction on the tibia. So I'm going to change that from 5 centimeters to 0, that means that the tibia will now insert in the center of the bone. And we can load that in, and we can go over here and we can run the analysis again. Oops, I just want to switch this one off. And we can run the analysis again. Inverse dynamic analysis, run. And now you can see the muscle is inserting in the center of the tibia. And immediately we are getting a horizontal displacement of inside the knee instead of the mostly vertical displacement that we were having before. And obviously this is because we have changed the insertion point of the tibia. So this is just a very simple example on how you can use this kind of technology to understand what goes on inside the model. Now imagine that you are building a knee prosthesis that had a certain geometry and certain stabilizing elements. And this was not a very simple model, but actually an anatomically realistic model of the knee like we have in our model repository. Of the lower extremity like we have in our model repository. And we subjected this to various activities of daily living rather than a simple extension like this one. Then we could actually study how the knee prosthesis would work under those conditions. And that is, of course, one of the purposes of building this technology that you see here. You can also see that it takes a little more time to do the analysis when we use the force-dependent kinematics than it does when we don't use it. And obviously that is true because there are some additional computations going on inside the system. But this is by no means prohibitive. You see, in just a few moments while I'm speaking, you can see that we can do the analysis of this case. So it's not actually prohibitive, and it is much faster than for instance, finite element analysis. So while this is analyzing, I'll just go back to the chart effect view and look at the positions again. And now you can see that the green and the red graph here both have significant values, and actually the red displacement, which is parallel to the tibial plateau, has a significant value. So this is about 3 or 4 centimeters at the moment. Now, that was the first example. So now I've shown you in much detail how to define these. There's one other thing that I would like to show you, and that is how to define surface contact points, or surfaces in contact. And I have a model that can be used to do that. I'm just going to close this down and then go over to this one instead. Now, this is a model that is much similar to the other one. In fact, if we load this, you will see on the model view here that it is very similar, so it actually looks exactly like the other one. But if we hide this condyle and we zoom in on the model, you will notice that there is something additional going on in here, inside the model. What you can see is that inside the model we now have a gray part here. And I'm going to switch off some more stuff so that we can easier see what that is. So we hide this, and then you can see that these are a couple of metal components that we have placed inside the knee. And these metal components are actually, they are not completely aligned now, they will be aligned in just a second. But there's a femoral component here, and there's a tibial component here. And in just a moment, when we run the analysis, these two components are going to be in contact with each other. And these are structured surfaces. They are made out of STL files, so they can have any surface geometry that you would like. And you can see that there's a little bit of curvature here on the tibial plateau, and that is going to come into contact with the curved surface here on the femoral part. Before we do so, let's just go into the model and see how this is done. So if we scroll down a little bit in the model, you can see many of the same components that we had before. But you can see here that we have defined an insert STL. This is the tibial part here. And also there is in the femur, there is up here an insert STL, which is the femoral head. And those are the two surfaces which have been imported. They are saved on STL files. You can see here is the name of the STL file of the femoral part. So the only thing you have to do this is actually to save those two STL files and then import them into the model like this. As we go a little bit further down, you can see that there is now an any force surface contact object defined here. And this object is defining one surface which is called the master surface, which is this one, and this is the femoral head. And then there's one surface which is called the slave surface, which is, in this case, is the tibial part. Now, what the system does when we have a couple of surfaces like that is that the system is detecting contact between these two parts, and to the extent that they are penetrating each other, it is going to generate contact forces between the two surfaces, and those contact forces are going to depend linearly on the penetrated volume, and the coefficient of elasticity for that computation is the one that you see here. So this is the way to make the materials for the two components more or less hard. Now it takes a bit more time to analyze this, so I have cheated just a little bit. I'm going to go into the model and the study, and then I'm going to read in some data that I analyzed earlier. So I'm going to load those, and we have them here. And now those are loaded, and that means I can run a replay of the model. So instead of doing the actual analysis, and that means that it will run much faster. So if we go here, we can try to single step through this. You see, if I make one step, the two parts will now come into contact with each other. And remember that the bones are also here. We have the femur and the tibia in the model, but I've just graphically switched them off so that we can see what is taking place. Then if we step here, you can see that now the two are beginning to move with respect to each other, depending on the contact forces between them. And if we just click play here, you will see we will get the whole analysis going on. And we can look at that from different sides, maybe a little bit more from over here. So you can get another vantage point. And you can see here how the two surfaces are sliding on each other while the contact is being calculated. In reality, it takes more time to do this than what you've seen here. This is just a replay of data that I did earlier. And of course, again, it takes some time to do the analysis, but it is definitely not an unfeasible amount of time. It is still something that you can do within a reasonable amount of time on a normal desktop computer. So with that, I would like to go back to the presentation and just kind of round things off. I would like to say that you can know much more about this technology if you go to AnyBodyTech.com. There you can get demo licenses for the AnyBody modeling system. If you want to do this particular thing, you might want to wait a few days until version 5.1 of the software will be released. And on that homepage, you can also sign up for the next webcast on September 29th, where we are going to try to use this technology on more anatomically realistic examples. There's another homepage that might interest you. This is Inscript.org. This is the community that we have of users of the AnyBody modeling system. There's a discussion forum where people are helping each other and asking questions about how to make models. There's a wiki part in which you can, for instance, upload your models or write stories about the stuff that you do. And there is a model repository part where you can always find the latest version of the AnyBody model repository. Finally, the university research project is also available at anybody.aau.dk. Now we've come to the question and answer session, and if any of you have any questions, please go to the little panel in your lower right-hand corner of the screen and click the question mark and then type in your question. Please remember to send it to host